In the dark canvas of the night sky, Betelgeuse shines as a true oddity. This giant star not only stands out because of its massive size and bright glow, but also because of its strange and unpredictable behavior. Its unusual dimming, slow spin, and mysterious changes have sparked the curiosity of both scientists and star lovers alike. Let's embark on a journey through the world of Betelgeuse and other colossal stars. We will explore how these massive stars live, change, and die. Join us on this deep dive into the mysteries of Betelgeuse and discover what makes it, and others like it, some of the most fascinating objects in our sky. The peculiar face of Betelgeuse. Why this star stands apart. Betelgeuse is one of the most famous stars in the night sky, easily visible as the bright reddish shoulder of Orion. Its presence in the constellation is unmistakable, and the star itself is extraordinary. It is a red supergiant, a type of star that has reached the final stages of its life, expanding to an enormous size before it eventually collapses. Yet, even among other supergiants, Betelgeuse stands apart. It is unpredictable, changing in brightness in ways that have puzzled scientists for centuries. Its surface is restless, with massive convective cells shifting like slow-motion storms. And in recent years, its behavior has grown even more mysterious, challenging what we thought we knew about dying stars. Unlike most stars that shine with steady, predictable light, Betelgeuse flickers and dims. This variability is not new. Astronomers have recorded changes in its brightness for over a century. But in late 2019 and early 2020, it did something unexpected. The star dimmed more dramatically than ever before, losing over 60% of its brightness. The event, known as the Great Dimming, sparked widespread interest. Some thought it was a sign the star was about to explode in a supernova, an event that would make Betelgeuse one of the brightest objects in the night sky. But instead, the star gradually returned to its usual brightness, leaving scientists with more questions than answers. Unlike our Sun, which has a relatively stable surface, Betelgeuse is covered in massive churning convective cells. These are vast regions where hot gas rises from the star's interior, cools, and then sinks back down. But while convection happens in many stars, the scale of these cells on Betelgeuse is extreme. Some of these structures are so large they could stretch across an entire planetary system. They cause the star's surface to shift and change over time, making it appear uneven, almost misshapen. This gives Betelgeuse a distinctive, irregular look that sets it apart from other red supergiants. It is a star in the final stages of its life, and as it nears the end, it sheds material into space. This creates a hazy environment around it, shaping the light that reaches us. This dust cloud is not uniform. It forms knots and clumps, creating shadows and irregular patterns. When the Great Dimming occurred, astronomers later determined that one likely cause was a massive outflow of gas from the star. This material cooled and condensed into a thick cloud of dust, blocking some of the light before eventually dispersing. The surface of Betelgeuse is also cooler than many other stars, which is part of what gives it its deep red color. Compared to the Sun, which has a surface temperature of about 5,500 degrees Celsius, Betelgeuse is much cooler, around 3,200 degrees. But even this temperature is not uniform across the star. Some regions are hotter, while others are much cooler. This variation contributes to its irregular brightness, as different parts of the star can change in intensity over time. Observations have even shown that Betelgeuse appears to boil as hot gas moves and cools across its surface. Betelgeuse is not a stationary object in the sky. It is moving at high speed through space. In fact, it is racing through the Milky Way at about 30 kilometers per second. As it moves, it creates a bow shock, a massive wave of material in front of it, like a ship cutting through water. This shockwave, detected in infrared light, shows how the star interacts with the surrounding interstellar medium. All of these factors combine to make Betelgeuse one of the most dynamic stars ever studied. Its surface is restless, its brightness unpredictable, and its surrounding environment complex and ever-changing. For centuries, it has fascinated people, and with each new discovery, it only becomes more mysterious. A supergiant among supergiants, Betelgeuse in context. Red supergiants are some of the most massive stars in the universe, yet they are also in a stage of life that marks their impending demise. Unlike main sequence stars like the Sun, which shine steadily for billions of years, red supergiants exist in a state of constant change. They have expanded to colossal sizes as they near the end of their lives, their outer layers swelling outward as the nuclear reactions in their cores shift. The result is a massive, luminous star that burns far more brightly than the Sun, but is also far less stable. Betelgeuse is estimated to have a mass between 15 and 20 times that of the Sun, but its volume is vastly larger. If it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Mars, possibly even reaching Jupiter. This immense size comes at a cost. Betelgeuse is burning through its fuel at an accelerated rate, and its days as a star are numbered. Compared to the Sun's lifespan of roughly 10 billion years, Betelgeuse's lifespan is only about 10 million years, much of which it has already lived through. In astronomical terms, that is incredibly brief, a fleeting existence for a star so massive. Despite its incredible size, Betelgeuse is not the largest red supergiant known. Other stars, such as VY Canis Majoris and UY Scuti, are estimated to be even larger. However, Betelgeuse is unique because of its extreme proximity to Earth. At only about 500 light-years away, it is one of the closest massive stars nearing the end of its life. This makes it an important target for study. While most red supergiants are so distant that they appear only as points of light, Betelgeuse is close enough that astronomers can actually observe its surface features. It is one of the very few stars for which scientists have been able to create detailed images, revealing an uneven shifting disk rather than a simple round shape. Even though it is some ways from Earth, it ranks among the brightest stars in the night sky, partly because it is naturally luminous and partly because of its proximity. If Betelgeuse were placed where the Sun is, it would be over 100,000 times more luminous. However, unlike many bright stars that shine with a consistent glow, Betelgeuse's brightness is highly unstable. It undergoes regular variations, dimming and brightening over months and years. These fluctuations are a result of the turbulent processes happening inside the star. Massive convection cells cause parts of Betelgeuse to brighten and darken at different times. Its outer layers are also constantly shifting, expanding and contracting in cycles that create unpredictable changes in its brightness. Antares, the bright red supergiant in the constellation Scorpius, shares many similarities with Betelgeuse in terms of color and size, but it does not exhibit the same level of irregularity. VI Canis Majoris is even larger and has been observed producing massive amounts of dust, but it is much farther away, making detailed observations more difficult. While it is clear that Betelgeuse will eventually explode as a supernova, the exact timing remains uncertain. It could happen within the next few thousand years, or it could still have tens of thousands of years left. When it does explode, the event will be one of the most spectacular celestial displays ever witnessed by humanity. For a brief period, the explosion will shine brighter than the full moon, casting shadows on Earth, before gradually fading over the course of months or years. Such an event would provide astronomers with an unprecedented opportunity to study a supernova up close. Its brightness and deep red color have made it a notable feature in the night sky for thousands of years. Ancient civilizations observed it, and many cultures linked it to myths, stories, and omens. Its position in the constellation Orion, one of the most recognizable constellations, has further cemented its place in astronomical history. The slow rotators versus the fast rotators, a study in extremes. The rotation speed of a star can reveal a great deal about its history, structure, and evolution. While some massive stars spin at breakneck speeds, completing a full rotation in just a few hours, others turn so slowly that their rotation is barely measurable. This vast difference in angular momentum among massive stars is one of the most striking contrasts in astrophysics. offering insight into the forces that shape their lives and their eventual fates. Slow rotators, like Betelgeuse, are unusual among massive stars. Betelgeuse rotates at an incredibly sluggish pace compared to many of its peers, with an estimated rotation speed of just a few kilometers per second at its equator. This is remarkably slow for a star of its size, especially when compared to other red supergiants that exhibit much faster rotation. The reason for this slow spin is likely connected to how Betelgeuse has evolved over time. As it expanded into a supergiant, its original angular momentum was spread over a much larger volume, drastically reducing its rotation speed. This is similar to how a spinning ice skater slows down when extending their arms outward. Additionally, interactions with a possible past companion star or mass loss events may have further reduced its rotational velocity. At the other end of the spectrum, some massive stars rotate at astonishing speeds. Stars like VFTS 102, a blue giant in the Large Magellanic Cloud, spin at over 500 kilometers per second at their equators. This rapid rotation creates extreme conditions in their atmospheres, causing their shapes to become highly distorted. Instead of being perfect spheres, fast rotators bulge outward at the equator due to centrifugal force, forming what astronomers call an oblate shape. The faster the rotation, the more pronounced this effect becomes. In the most extreme cases, a star's outer layers can become so loosely bound that material escapes into space, forming a surrounding disk of gas. Antares, another red supergiant often compared to Betelgeuse, rotates much faster than its more famous counterpart. While still slow by the standards of smaller stars, Antares exhibits a noticeable rotation rate that distinguishes it from Betelgeuse. The reason for this difference is not entirely clear, but it may be due to the way Antares retained more of its original angular momentum during its transformation into a supergiant. Many of the fastest rotating massive stars are part of binary systems, where the gravitational pull of a close companion can either speed up or slow down the primary star's rotation. In some cases, mass transfer between two stars in a binary system can result in a dramatic increase in rotational speed. When one star donates material to another, it can act like a cosmic push, transferring angular momentum and accelerating the receiving star's spin. Faster rotation leads to stronger mixing of elements in a star's interior, altering how nuclear fusion progresses and potentially extending the star's life. Rotation also influences the type of supernova a star will eventually undergo. A rapidly spinning star can explode in a much more asymmetric manner, producing powerful jets, and even leading to the formation of gamma-ray bursts, some of the most energetic events in the universe. In contrast, slow rotators like Betelgeuse may experience a more traditional collapse, where the explosion is largely spherical and symmetrical. Fast-spinning stars tend to experience stronger equatorial mass loss, as their outer layers are more loosely bound. This means that some of the most rapidly rotating stars might shed more material before reaching the end of their lives, affecting the size and shape of the nebula they create. Meanwhile, slow rotators like Betelgeuse lose mass in a more uniform pattern, forming large spherical shells of ejected gas. The study of stellar rotation is still evolving, with new discoveries continuing to refine our understanding of how and why these differences occur. Advances in observational techniques, including interferometry and high-resolution spectroscopy, have allowed astronomers to measure the rotation speeds of distant stars with greater accuracy than ever before. The mystery of Betelgeuse's slow spin versus Antares' rapid rotation. Betelgeuse's rotation is so slow that it is difficult to measure precisely. Estimates suggest it spins at roughly 5 kilometers per second at its equator, an almost imperceptible pace compared to many other massive stars. Antares, on the other hand, has a rotation speed closer to 20 kilometers per second, still slow compared to main sequence stars, but notably faster than Betelgeuse. This difference might seem small, but in astrophysical terms, it hints at fundamental differences in their pasts. When a star forms from a collapsing cloud of gas, its spin rate depends on how much rotational motion was present in the original cloud. Some stars are born with more angular momentum than others, setting the stage for differences that persist throughout their lives. However, that alone does not explain why Betelgeuse and Antares have such different rotation rates today, since they are similar in mass and have both expanded into red supergiants. As a star evolves, its rotation slows dramatically. Both Betelgeuse and Antares have undergone this process, which suggests that some additional mechanism has acted more strongly on Betelgeuse to reduce its spin. One possibility is mass loss. Red supergiants shed enormous amounts of material through powerful stellar winds, and this process can also carry away angular momentum. Betelgeuse is losing mass at an extraordinary rate, far faster than Antares. Observations show that Betelgeuse has shed a significant amount of its outer layers in the past few centuries alone, producing vast clouds of dust and gas that obscure parts of its surface. This high mass loss rate might have played a key role in slowing Betelgeuse's spin, as the ejected material would have carried away rotational energy along with it. If Betelgeuse once had a close companion that merged with it, the merging process could have disrupted its angular momentum, slowing its spin significantly. Alternatively, if Betelgeuse lost a companion star due to gravitational interactions, that event could have also removed a large amount of rotational energy from the system. Antares, in contrast, is part of a binary system with a known companion, Antares b. While this companion is much smaller and does not significantly affect Antares' structure today, it suggests that Antares may have experienced a different evolutionary history than Betelgeuse. If Antares never underwent a major merger event or a drastic angular momentum loss due to mass ejections, it could have retained more of its original spin. Magnetic fields also play a role in stellar rotation. As stars expand, their magnetic fields can interact with surrounding plasma, creating a braking effect that gradually slows rotation. This is known as magnetic braking, and it is commonly observed in smaller stars like the Sun. While red supergiants like Betelgeuse and Antares do not have strong magnetic fields compared to younger stars, there is some evidence that residual magnetism could still influence their spin rates. If Betelgeuse's field is slightly stronger than Antares, it might have experienced greater rotational braking over time. Despite their similarities, these two red supergiants have taken very different paths, shaped by factors such as mass loss, possible past companions, magnetic fields, and internal convection. Understanding these differences sheds light on the broader processes that govern the lives of the most massive stars in the universe. Canis Majoris, a star in the process of tearing itself apart. It's interesting to compare Betelgeuse to some of the other largest known stars in order to get a sense of the diversity among the group. Canis Majoris is classified as a red hypergiant, a rare category of stars even larger and more unstable than red supergiants. Located about 3,900 light-years away in the constellation Canis Major, it is one of the biggest and most luminous stars ever discovered, with a radius potentially double that of Betelgeuse, though its exact size is difficult to measure. Unlike Betelgeuse, which still retains some stability, Canis Majoris is in a state of near-complete disintegration, shedding enormous amounts of material into space as it nears the end of its life. Observations show that the star is surrounded by thick clouds of gas and dust, ejected over thousands of years. These massive outflows are evidence of extreme instability, with the star losing mass at an astonishing rate. In some regions, this expelled material forms structures resembling arcs and knots, created by violent bursts of energy from the star's surface. Unlike Betelgeuse, which has a more defined, though turbulent, outer shell, Canis Majoris is surrounded by a dense and complex nebula, the result of its ongoing self-destruction. Canis Majoris has been observed to lose several times the mass of the Sun in just the past few thousand years. This extreme mass loss is driven by powerful stellar winds, which blow material away at speeds of tens of kilometers per second. Scientists believe that these winds are fueled by strong convection currents beneath the star's surface, creating unstable layers that eventually break apart and escape into space. As these convective plumes burst outward, they carry significant portions of the star's mass with them, adding to the surrounding nebula. Like Betelgeuse, it is a variable star. However, while Betelgeuse's dimming episodes tend to follow somewhat predictable cycles, Canis Majoris experiences dramatic and irregular changes. These sudden variations are linked to the vast amounts of material it expels. When thick clouds of dust and gas move in front of the star, they block some of its light, causing its brightness to drop. As the material disperses, the light can increase again, but the process is chaotic, making it difficult to predict how the star will behave over time. The mass loss experienced by Canis Majoris is so extreme that some scientists believe it is skipping the normal supergiant phase entirely, heading straight into its final collapse. Most massive stars gradually transition through different stages before exploding in a supernova, but Canis Majoris may be shedding so much mass that it won't have enough material left to trigger a traditional supernova explosion. Instead, some models suggest that it could collapse directly into a black hole, bypassing the bright explosion that usually marks the end of a star's life. If this happens, Canis Majoris may one day simply vanish from the sky, leaving behind only an expanding shell of gas and a newly formed black hole in its place. Unlike most stars, which are roughly spherical, Canis Majoris appears to be asymmetrical. The intense mass loss is not evenly distributed across the star's surface, meaning that some parts of the star are shedding material faster than others. This creates a distorted appearance, with sections of the star expanding outward more rapidly, forming complex patterns in the surrounding nebula. This irregular shape contrasts with Betelgeuse, which, despite its instability, still maintains a roughly spherical form. The study of Canis Majoris's extreme instability offers a glimpse into the final stages of a star's life, showing what happens when a massive star loses control over its own structure. Observations of the material ejected from the star help astronomers understand the process of mass loss in hypergiants, which in turn affects the evolution of galaxies. The heavy elements produced in such stars are eventually scattered across space, contributing to the formation of new stars and planets. Despite its immense size and luminosity, Canis Majoris is not easily visible to the naked eye. Its brightness is heavily affected by the surrounding dust, making it appear much dimmer than it actually is. Without this dust, it would shine far more brightly in the night sky, potentially rivaling some of the most prominent stars. Will it explode in a spectacular supernova, or will it collapse quietly into a black hole? How long can it sustain its massive outflows before its core becomes unstable? These questions make Canis Majoris one of the most important stars to observe in the coming years in our quest to understand the wild lives of the largest stars in the universe. Cephei and its faint but immense presence. Cephei, often called the Garnet Star because of its deep reddish hue, is one of the largest known stars in the universe at around 1,000 times the radius of the Sun, putting it somewhere between Betelgeuse and Canis Majoris. Located in the constellation Cepheus, Cephei is positioned near the edge of what the human eye can easily perceive. Even though it is among the most luminous stars known, its distance of around 2,800 light-years makes it appear fainter than many other, less impressive stars. If placed in the solar system, it would extend beyond the orbit of Jupiter. It is a variable star, but its dimming and brightening happen in a way that is not as sudden or irregular as Betelgeuse's. This makes it less of a spectacle, even though it is still evolving towards an eventual fate as a supernova. Its rich red tone is noticeable even without a telescope, which is rare for stars. Most stars, including red giants, appear white or slightly orange to the naked eye, but Cephei has a deep crimson color that sets it apart. This striking hue comes from its relatively low surface temperature and the way its outer layers scatter light. It is cooler than many other supergiants, but its immense size allows it to radiate enough energy to outshine thousands of ordinary stars combined. Stars of this type are in a highly unstable phase where nuclear fusion is pushing against gravitational collapse in a delicate balance. The outer layers of Cephei are slowly being pushed away by the force of its own radiation, forming a surrounding cloud of material that will eventually enrich space with heavy elements. Over time, this star will continue to lose mass, shaping the environment around it as it progresses toward its explosive end. Unlike some of the more famous supergiants, Cephei does not seem to have undergone any major unexpected changes. It has remained relatively stable compared to Betelgeuse, which has gone through dramatic dimming events, and Canis Majoris, which is actively shedding vast amounts of mass in a chaotic manner. Cephei's steadier nature makes it a valuable object of study, offering astronomers a chance to observe a massive star in a phase that is somewhat calmer. While Betelgeuse is part of Orion, one of the most well-known constellations, Cephei is in Cepheus, which is not as immediately recognizable. This makes it less of a focal point for amateur stargazers. Observing Cephei offers a contrast to the more volatile examples seen elsewhere in the universe. When do these supergiants stop growing? Supergiants are among the most massive and luminous objects in the universe, but they do not keep growing indefinitely. There is a point where their size and mass reach a limit, governed by the forces at work inside them. The balance between gravity pulling inward and the energy from nuclear fusion pushing outward determines how large a star can get. When this balance is disrupted, the star stops growing and its fate begins to change. When a massive star first forms, it begins by fusing hydrogen into helium, just like smaller stars such as the Sun. But supergiants consume hydrogen at an incredible rate. Their extreme size and temperature make fusion happen at much higher speeds, causing them to burn through their fuel thousands of times faster than stars like the Sun. Because of this, supergiants do not remain in the hydrogen-burning phase for long. As the hydrogen supply begins to run low, the core contracts under its own weight. This contraction causes the temperature and pressure inside the star to rise dramatically. As a result, new fusion reactions begin, allowing the star to burn heavier elements such as helium, carbon, and oxygen. Each time a new element is fused, the energy released forces the outer layers of the star to expand. This is why supergiants grow larger as they age. However, this expansion cannot continue indefinitely. The cycle of contraction and expansion continues only as long as there is a new element that can be burned for energy. Once the core reaches iron, fusion can no longer produce enough outward pressure to support the star's immense mass. Unlike the reactions before it, which generated the power needed to counteract gravity, iron fusion does not provide a net energy gain. This marks the end of the star's growth phase, as no further fusion can prevent the force of gravity from taking over. Even before reaching this stage, other processes can prevent a supergiant from growing any larger. One of the most important factors is mass loss. Unlike smaller stars, which gradually lose material over billions of years, supergiants shed their outer layers much more violently through a variety of previously mentioned processes. These processes prevent the star from continuously expanding by removing mass from its outer layers. In the most extreme cases, mass loss can actually cause a supergiant to shrink instead of grow. If a star loses too much material, its remaining core becomes exposed, revealing a much smaller but incredibly hot object. Some red supergiants transition into blue supergiants this way, appearing more compact and luminous than before. Others lose so much mass that they skip their final expansion phase entirely, collapsing more quickly than expected. Stars that form in dense clusters or near energetic objects like black holes and pulsars are often influenced by external forces. Intense radiation from neighboring stars can strip away material, preventing further expansion. Gravitational interactions with other stars can also disrupt the growth cycle, causing the supergiant to lose mass more quickly. If a supergiant has a close companion star, that companion can siphon off material, significantly altering its evolutionary path. Betelgeuse is believed to be nearing the end of its growth phase. These changes indicate that it is transitioning from a stable red supergiant into a more unstable state, eventually leading to its collapse. One of the most important tools for studying when supergiants stop growing is spectroscopy. By analyzing the light emitted by these stars, astronomers can determine their composition, temperature, and movement. This allows them to track changes in the star's structure and activity over time. When a supergiant's outer layers begin to thin, changes in its spectrum can reveal how fast mass is being lost and what elements are present in its atmosphere. These clues help scientists determine how much longer a supergiant will remain in its current state before it begins the final stages of its life. Another method used to study them is long-term brightness monitoring. Supergiants often vary in brightness, so by tracking these variations over months and years, astronomers can identify patterns that signal the end of a star's expansion phase. In some cases, sudden dimming events can indicate that the star is shedding large amounts of material in preparation for collapse. By simulating the physics of stellar interiors, scientists can test different scenarios to understand how stars evolve. These models take into account factors like mass, temperature, composition, and rotation speed to determine how a star's life cycle will unfold. Comparing these models to real-world observations allows astronomers to refine their understanding of supergiant evolution. One surprising discovery from these models is that not all supergiants follow the same path. Some stars, despite being massive enough to become red supergiants, never reach that stage due to rapid rotation or magnetic fields. Others may lose mass so quickly that they transition into a completely different type of star before reaching their final stages. These variations show that while the general rules of stellar evolution apply to most supergiants, each individual star has a unique journey. The end of a supergiant's growth is not the end of its story. Once a star reaches this phase, the countdown to its final collapse begins. Whether it undergoes a violent supernova explosion or takes a less dramatic path, its fate is sealed. The point at which expansion stops is a critical moment, setting the stage for the most extreme transformations in the universe. The paradox of low-density giants, why they are vast but thin. Some of the largest stars in the universe have a physical structure that is far less dense than one might expect. This creates a striking contrast. These stars are enormous in volume but, at the same time, surprisingly thin in terms of material concentration. Understanding why these stars are so vast but diffuse requires a deeper look into their internal structure and the forces that shape them. Stars are held together by a balance of two opposing forces. Gravity pulls inward, trying to collapse the star under its own weight, while the energy from nuclear fusion pushes outward, preventing it from collapsing. In supergiants, this outward pressure is much stronger than in smaller stars, causing their outer layers to expand dramatically. But as these outer layers stretch across a massive volume, the material within them becomes increasingly sparse. This is why supergiants, despite their immense physical size, can have lower densities than many compact stars. Although Betelgeuse is over 700 times the radius of the Sun, its average density is astonishingly low. Betelgeuse's outer layers would extend beyond Jupiter, but the gas in these layers is so thin that if you were to travel through the star's outer atmosphere, you would find it less dense than the air on Earth. The reason for this lies in the way heat and energy move through the star. Unlike in smaller stars, where energy is transported efficiently through dense layers, supergiants have vast convective zones where hot gases rise and fall in enormous currents. These motions create instability in the outer regions, causing the star to appear bloated and diffuse. Another factor is their advanced stage of evolution. When a star reaches the supergiant phase, it has already burned through much of its hydrogen fuel. As a result, its core contracts under gravity, becoming smaller and denser, while the outer layers expand outward. This expansion spreads the star's mass over an enormous area, further reducing its overall density. Because of this, a red supergiant like Betelgeuse is much less dense than a younger, main-sequence star of similar mass. Low-density supergiants are highly unstable. Their outer layers are not tightly bound to the core, making them more susceptible to losing mass through stellar winds and eruptions. VY Canis Majoris, another extreme example, is even larger and more diffuse than Betelgeuse. It has an incredibly extended atmosphere filled with unstable gas and dust. Observations show that its outer layers are being continuously expelled, forming a massive nebula around the star. The density of its outer envelope is so low that material from deep within the star can be lost into space without much resistance. A neutron star can have a mass greater than the Sun, but be compressed into an area no larger than a city. In contrast, a red supergiant can have hundreds of times the Sun's mass, yet be spread across an enormous volume. Similarly, a single teaspoon of white dwarf material would weigh several tons on Earth. Meanwhile, a teaspoon of material from a red supergiant's outer atmosphere would be barely noticeable, as it would contain only a few particles of gas. This highlights the wide range of densities found in the universe and shows how the size of a star does not always reflect how tightly packed its material is. The more diffuse a star becomes, the more vulnerable it is to rapid collapse. When fusion in the core can no longer support the star's weight, gravity takes over almost instantly. Because the outer layers are so extended, they collapse inward at high speeds, triggering a massive explosion in the form of a supernova. This event marks the dramatic end of the star's existence and disperses its material out into space. Is Betelgeuse a runaway star? Its curious motion through space. While Betelgeuse might appear motionless in the night sky, it is actually racing through space at an incredible speed. Observations have shown that it is moving at about 30 kilometers per second relative to its surroundings. This movement is fast enough that over thousands of years, its position shifts noticeably against the background stars. Unlike many stars that remain in relatively fixed positions within their birthplaces, Betelgeuse appears to be a runaway, an object that has been ejected from its original home and is now traveling independently through the galaxy. A clue to Betelgeuse's motion comes from the massive bow shock it leaves behind. A bow shock forms when a fast-moving star plows through interstellar gas, compressing it into a curved, wave-like structure ahead of the star. In the case of Betelgeuse, this shockwave extends several light-years in front of it. Infrared images from space telescopes reveal this bow shock in vivid detail, showing a curved shell of gas and dust that Betelgeuse is actively pushing through. This suggests that the star is moving through space at a high velocity, much like a speeding boat creating waves as it moves through water. The big question is, why is Betelgeuse moving so fast? Most stars remain close to the regions where they were born, orbiting within their galaxies at stable speeds. For a star to become a runaway, something must have given it an extra push. There are a few possible explanations. One is that Betelgeuse was once part of a binary system. If its companion exploded in a supernova, the sudden loss of mass could have sent Betelgeuse hurtling away at high speed. This kind of event has been observed in other runaway stars, where the explosion of one star disrupts the balance and flings the survivor outward. If Betelgeuse was once bound to another massive star, it might have been ejected when that star met its end. Another explanation is that Betelgeuse was kicked out by gravitational interactions within its original star cluster. Stars do not form in isolation. They emerge in groups, clustered together in vast nurseries of gas and dust. Within these clusters, stars constantly interact with one another, and sometimes these interactions result in dramatic ejections. If Betelgeuse once belonged to a crowded star-forming region, a close encounter with other massive stars could have slingshotted it into its current motion. Tracing Betelgeuse's origins is difficult because it is an old star that has traveled far from where it was born. However, astronomers have attempted to determine its birthplace by studying its motion and working backward. Some estimates suggest that Betelgeuse may have originated in the Orion OB1 association, a region of hot young stars located near the famous Orion Nebula. If this is correct, then Betelgeuse has been traveling for millions of years, steadily moving away from the place where it first formed. Understanding its past travels could provide more insights into where it came from, what interactions it experienced, and how its motion will influence the final stages of its life. Unlike stars that remain within their birthplaces until they explode, Betelgeuse appears to be living a more solitary existence, having left its origins behind long ago. The 2019 Great Dimming. What really happened? In late 2019, Betelgeuse began to fade. Over the next few months, its brightness dropped to nearly 40% of what it had been before. By early 2020, Betelgeuse looked significantly dimmer than usual, even to the naked eye. Astronomers around the world took notice. The change was so dramatic that some began to wonder if this was a sign that the star was about to explode. Betelgeuse, at some point in the future, will run out of fuel, collapse under its own gravity, and explode as a supernova. While this could happen within the next 100,000 years, no one knows exactly when. The sudden dimming in 2019 led some to speculate that the star was entering its final phase. However, as more observations were collected, it became clear that something else was happening. Astronomers quickly proposed two main explanations. One was that Betelgeuse's surface was undergoing changes due to the natural convective processes inside the star. The other was that a cloud of dust had formed in front of Betelgeuse, blocking some of its light. Both ideas had merit, and scientists worked to figure out which one was responsible. Betelgeuse's surface currents bring hot gas from the star's interior to the surface, where it cools and sinks back down. If one of the cells changed in a way that made part of the surface cooler, it could have caused the dimming. This would mean that Betelgeuse's brightness didn't actually decrease overall, but rather that one side of the star became significantly darker. The other explanation involved dust. Expelled material containing elements like carbon, silicon, and oxygen can form tiny solid particles, essentially cosmic dust. If Betelgeuse ejected a large cloud of material, it's possible that the dust condensed and temporarily blocked the star's light from reaching Earth. To determine which explanation was correct, astronomers turned to different types of telescopes. The Hubble Space Telescope observed Betelgeuse in ultraviolet light, while ground-based telescopes studied it in infrared. Ultraviolet observations revealed a massive outflow of hot gas from the star's surface in mid-2019, months before the dimming was noticed. Infrared observations later showed that a cloud of dust had formed in the same region. This provided strong evidence that the dimming was caused by a dust cloud. The likely sequence of events was that Betelgeuse ejected a large portion of its outer atmosphere, possibly due to a powerful convective surge. As this gas moved away from the star, it cooled and condensed into dust. This cloud of material then partially obscured Betelgeuse from our view, making it appear dimmer. While dust was the primary cause, some astronomers believe that internal changes also played a role. This would explain why the dimming wasn't uniform across the star's surface and why it appeared asymmetric in some telescope images. The event provided astronomers with a rare opportunity to study a red supergiant undergoing a major transformation in real time. Betelgeuse eventually returned to its normal brightness by mid-2020, but the event left many questions unanswered. If the star could expel such a massive amount of material once, it could happen again. Some wonder if these periodic ejections are a sign that Betelgeuse is nearing the end of its life, though most experts believe that it still has thousands of years left. Betelgeuse is one of the best studied stars, and yet similar events might be occurring in other supergiants without our noticing them. The transient nature of these phenomena means that they could be missed unless astronomers are continuously monitoring the stars. This has led to a push for more frequent and higher resolution observations of red supergiants. using a range of wavelengths to capture all aspects of their behavior. While the full story of Betelgeuse's behavior is still being written, events like the Great Dimming offer us a unique window into the heart of this dying star. Does Betelgeuse have a hidden companion? The unresolved binary mystery. Betelgeuse is exceptionally well studied, yet some of its fundamental properties remain uncertain. One major unresolved question is whether Betelgeuse has a hidden companion. Some evidence suggests that this red supergiant may not be alone, but confirming the presence of a binary partner has proven to be a difficult challenge. Many massive stars are part of binary or multiple star systems, and recent studies suggest that most red supergiants were originally in binary pairs before their outer layers expanded. A companion could explain some of Betelgeuse's unusual behaviors, such as its asymmetric mass loss, irregular surface activity, and the way its motion through space appears to be influenced by an unseen force. However, no companion has been directly observed. One reason why detecting a companion is difficult is that Betelgeuse is an enormous star with a vast extended atmosphere. A companion star, if it exists, would likely be lost in the bright glare of Betelgeuse's outer layers. Even powerful telescopes struggle to separate the light from a possible secondary star because Betelgeuse itself is constantly changing. Its surface boils with massive convective cells, and it periodically expels gas and dust, creating an environment where a small or faint companion could remain hidden. Despite these challenges, several pieces of indirect evidence do hint at the presence of another object. Some studies suggest that Betelgeuse's movement is not entirely smooth, as if it is being influenced by an unseen gravitational force. If Betelgeuse had a companion orbiting it at a relatively close distance, their mutual gravitational pull could create subtle shifts in its motion that could be detectable over time. Another clue comes from observations that Betelgeuse's mass loss appears to be uneven and directional rather than symmetrical. Some astronomers believe that a hidden companion could be disturbing the outflow of gas, shaping the material into patterns that would not form naturally around an isolated star. If a companion were orbiting close enough, it could be pulling material from Betelgeuse's outer layers, forming an accretion disk or a trailing stream of gas that could affect the way Betelgeuse appears. One theory proposes that Betelgeuse may have once been part of a binary system, but lost its companion due to a merger. In this scenario, Betelgeuse and a smaller star may have spiraled inward and eventually merged into a single, more massive star. While most of the evidence remains circumstantial, there have been a few attempts to search for one directly. Some astronomers have used high-resolution imaging techniques to look for a faint star near Betelgeuse, but these efforts have not yet provided a definitive answer. Betelgeuse's own brightness and variable outer layers can obscure any smaller objects nearby. However, ongoing advances in telescope technology, such as improved adaptive optics and future space telescopes, may eventually provide the resolution needed to detect a possible companion if it exists. If a companion were close enough, it might steal material from Betelgeuse, altering the way the star loses mass and potentially changing the conditions for its eventual supernova. In some cases, a close binary system can even produce an unusual type of explosion, such as a stripped envelope supernova, where the outer layers of a star are removed before it collapses. If Betelgeuse's companion has played a role in shaping its evolution, it could help astronomers refine their models of how massive stars end their lives. Can supergiants like Betelgeuse form planets? Planets typically form around young, stable stars, where a disk of dust and gas has time to settle and coalesce into planets over millions of years. Supergiants are violent, short-lived, and unstable, shedding mass at an extraordinary rate. Their powerful radiation and stellar winds disrupt anything around them, making it difficult for a traditional protoplanetary disk to exist. However, while conditions may not favor planetary formation in the way we usually imagine, there are still interesting possibilities to consider. Massive stars are born in regions filled with gas and dust, much like their smaller counterparts. If a star as massive as Betelgeuse had a disk early in its life, before it expanded into a red supergiant, it is possible that some solid bodies could have formed. The intense radiation from a massive young star, however, tends to blow away lighter materials, making it difficult for small, rocky planets to survive. The remaining material would need to be dense enough to resist the constant bombardment of high-energy particles and strong stellar winds. If any planets did form around Betelgeuse before it became a red supergiant, their fate would be grim. As the star expanded, it would have engulfed the inner planets in its system, vaporizing them in its growing outer layers. Any remaining planets farther out would be subjected to extreme stellar winds, disrupting their atmospheres and potentially stripping them of any gas they might have had. The gravity of Betelgeuse also changes as the star loses mass, altering the orbits of any surviving planets and possibly ejecting them into interstellar space. Despite these hostile conditions, there are ways in which planets could exist around a star like Betelgeuse, though they would be unlike the planets we see around stars like the Sun. One possibility is the formation of second-generation planets, objects that emerge from the material the star has already lost. As Betelgeuse sheds its outer layers, the expelled gas and dust could create a temporary disk around the star. In theory, this material could cool and clump together, forming new planetary bodies. These would not be planets in the traditional sense, since they would form late in the star's life, but they could resemble the small, icy worlds found in the outer reaches of our solar system. The galaxy is also filled with free-floating planets that have been ejected from their original solar systems. If one of these planets passed close enough to Betelgeuse, the star's gravity could have pulled it into orbit. However, the chaotic environment of a supergiant star makes it difficult for a captured planet to remain in a stable orbit for long. Most of the techniques astronomers use to detect exoplanets, such as the transit method or radial velocity measurements, work best with smaller, stable stars. A star as large and irregular as Betelgeuse produces too much noise, making it difficult to spot small objects in its vicinity. Additionally, any planets that might exist would likely be hidden within the thick clouds of gas and dust surrounding the star. Some astronomers speculate that large planets could survive in distant orbits around massive stars, far enough away that they are not directly affected by the star's expansion. These planets would have to be massive themselves, possibly gas giants or even brown dwarfs, which are objects too small to ignite fusion like a star, but too large to be considered typical planets. Brown dwarfs are fairly common, with perhaps as many as 100 billion located in the Milky Way alone, so that would not be too unusual. Once Betelgeuse reaches the end of its life and explodes in a supernova, any existing planets in its system would face an entirely new challenge. The explosion would release an enormous amount of energy, obliterating anything nearby. However, planets that are far enough away could survive, though they would be subjected to intense radiation and powerful shockwaves. Some of these planets could even be flung into deep space, becoming rogue planets themselves. The material from the supernova could contribute to future planet formation. The elements produced in Betelgeuse's final moments will mix with interstellar gas, seeding the next generation of stars and planets. In this way, while planets may struggle to form around a supergiant during its lifetime, the star's death plays a critical role in shaping future planetary systems elsewhere in the galaxy. The unpredictable winds of red supergiants. Mass loss on a massive scale. Massive stars are in a perpetual state of shedding material, their outer layers peeling off into space in a slow but relentless process. The winds of a red supergiant, though invisible to the human eye, are among the most powerful forces shaping the star's eventual fate. Unlike the strong but steady solar wind produced by stars like the Sun, the mass loss from a supergiant is chaotic, unpredictable, and extreme. The sheer scale of material being lost is staggering. A star like Betelgeuse ejects an amount of mass equal to Earth's entire atmosphere every year. Over the course of its life as a red supergiant, it could lose several times the mass of the Sun. The process is driven by multiple factors, including the star's unstable outer layers, radiation pressure, and the immense convective motions occurring beneath its surface. Unlike smaller stars, where mass loss is primarily driven by fusion at the core, red supergiants lose material in an irregular, almost turbulent manner, with some regions of the star ejecting more than others. In stars like Betelgeuse, convection occurs on a vast scale, with individual convective cells spanning a significant fraction of the star's surface. These cells churn, rise, and fall in cycles, but the low surface gravity of a supergiant means that some of this material is not pulled back inward. Instead, it escapes entirely, drifting off into space in the form of stellar wind. The larger and more unstable these convective cells become, the greater the mass loss. At the enormous luminosities of red supergiants, the outward pressure from radiation can overcome the gravitational pull of the star. This means that layers of gas at the surface can be pushed away, forming expanding shells of material that drift outward. Over time, this creates an envelope of dust and gas surrounding the star. In some cases, these ejected shells may remain loosely bound to the star, forming complex and dynamic structures in its immediate vicinity. The speed at which this material escapes varies. Some winds are relatively slow, moving at just a few kilometers per second, while others reach speeds of over 100 kilometers per second. This variation in wind velocity can lead to interesting interactions. Faster moving winds can catch up to and collide with slower moving material, creating shock waves that further shape the surrounding nebula. These interactions are important because they influence how the star's mass loss is distributed into space, ultimately affecting the kind of explosion it will undergo at the end of its life. While red supergiants are not known for having strong magnetic fields like smaller, more compact stars, some evidence suggests that they do play a role in mass loss. Magnetic loops and structures at the surface may help channel material outward, creating preferred directions for mass ejection. This could partly explain why some red supergiants, like VY Canis Majoris, have asymmetrical envelopes of expelled material rather than smooth, spherical distributions. As the star sheds its outer layers, its core becomes exposed to greater pressures, altering the nuclear reactions taking place within. Over time, this mass loss can determine how and when a red supergiant will reach the point of collapse. A star that loses mass too quickly may avoid a direct supernova explosion, instead transitioning into a different kind of stellar remnant. Conversely, a star that retains more of its outer layers may undergo a more dramatic explosion. The role of metallicity in shaping the biggest stars. The biggest stars in the universe are shaped by more than just their mass and temperature. Their chemical composition plays a crucial role in their evolution, influencing everything from how they burn fuel to how they shed mass and eventually die. This chemical makeup is known as metallicity, the proportion of elements heavier than hydrogen and helium present in a star. While massive stars are primarily composed of these two lightest elements, even small amounts of heavier elements can have a profound impact on their structure and behavior. The differences in metallicity across stars can lead to drastically different lifetimes, surface conditions, and even the nature of their eventual deaths. Metallicity is measured in relation to the Sun, which contains about 2% of its mass in elements heavier than helium. Stars with a higher proportion of these elements are considered metal-rich, while those with lower proportions are metal-poor. This classification has nothing to do with actual metals in the conventional sense. In astronomy, any element heavier than helium, including carbon, oxygen, and even lithium, the third lightest element, is grouped under the term metals. For the largest stars in the universe, metallicity is a key factor in how they interact with their surroundings and how they evolve over millions of years. The strength of stellar winds is closely linked to metallicity. Higher metallicity means more radiation pressure on the star's outer layers, increasing the rate at which it loses mass. This happens because metals in the outer layers absorb and scatter radiation more efficiently than hydrogen or helium, allowing photons to transfer momentum to the gas and push it away from the star. As a result, metal-rich stars shed more mass over time, sometimes losing a significant fraction of their original material before they reach the end of their lives. A metal-rich supergiant will gradually lose layers of its atmosphere, reducing its final mass before it collapses. In contrast, a metal-poor giant will hold on to more of its original mass because it experiences weaker stellar winds. This means that two stars born with the same mass but with different metallicities may end up having very different lifespans and fates. A high metallicity star might evolve into a stripped-down core that produces a relatively weak supernova, while a low metallicity star might retain more of its mass and collapse more violently, potentially forming a black hole instead of a neutron star. Metal-poor stars tend to be hotter and more luminous than metal-rich stars of the same mass. This is because metals contribute to opacity, the ability of a star's outer layers to block radiation. When a star has fewer heavy elements, its outer layers are more transparent, allowing more radiation to escape and raising its overall brightness. This effect is particularly noticeable in very massive stars, where small differences in opacity can significantly alter how energy is transported through the star. The influence of metallicity is also apparent in how stars move through different evolutionary phases. Stars with low metallicity tend to have a more extended main sequence phase, the period where they fuse hydrogen into helium, because their cores remain hotter and more stable. This means they burn their fuel more efficiently, delaying their transition into a supergiant phase. High metallicity stars, on the other hand, burn through their fuel at a slightly faster rate due to increased energy loss from their more opaque outer layers. This can cause them to expand and evolve more quickly, shifting into a red supergiant phase earlier than a low metallicity counterpart of the same initial mass. In the Milky Way, metallicity varies depending on location. Stars in the galactic center tend to be more metal-rich because they formed from material that had already been enriched by previous generations of stars. In contrast, stars in the outer regions of the galaxy and in some globular clusters are often metal-poor because they formed from less processed material. This variation means that massive stars in different parts of the galaxy may behave differently, even if they started with the same mass. Looking beyond our galaxy, some of the most metal-poor stars ever discovered are found in the early universe. The first generations of stars, known as population 3 stars, were almost entirely composed of hydrogen and helium, with virtually no metals present. These ancient stars, which formed just a few 100 million years after the Big Bang, were likely much more massive than most stars today, and burned through their fuel extremely quickly. Because they lacked metals, their stellar winds were weak, allowing them to hold on to most of their mass until they exploded as hypernovae, far more powerful than anything seen in the modern universe. While none of these population 3 stars have been directly observed, their effects can still be seen in the chemical composition of ancient stars that followed them. Betelgeuse itself has a metallicity slightly below that of the Sun, which suggests it formed in an environment with a slightly lower abundance of heavy elements. This could have influenced its mass loss history and contributed to its current state as a bloated, unstable supergiant. If Betelgeuse had formed with a much higher metallicity, it might have lost even more of its outer layers by now, possibly evolving into a different type of star altogether. On the other hand, if it had formed with much lower metallicity, it might have retained more of its mass and had a more prolonged evolution before reaching this final stage. When a massive star collapses in a supernova, the explosion itself is influenced by the star's metallicity. A high metallicity star that has lost much of its mass before collapsing may produce a weaker explosion, while a low metallicity star with more mass still intact might experience a more energetic and asymmetric explosion. The elements produced in the explosion then enrich the surrounding space, gradually increasing the metallicity of future generations of stars. This cycle of stellar birth death, and chemical enrichment is what drives the evolution of galaxies over billions of years. By analyzing the light from distant stars and measuring their chemical composition, astronomers can better predict how different types of stars will evolve and what kinds of remnants they will leave behind. Some of the biggest mysteries in astrophysics, such as the formation of black holes, the origins of heavy elements, and the nature of the first stars in the universe, are deeply tied to the role of metallicity. The atmosphere of Betelgeuse, stranger than science predicted. While red supergiants are expected to have complex and dynamic outer layers, Betelgeuse's atmosphere presents challenges that go beyond what standard models predict. Unlike smaller stars with well-defined outer boundaries, Betelgeuse has an extended, multi-layered atmosphere that appears to change shape, expand unpredictably, and release enormous amounts of material in ways that remain unexplained. While the star itself is already enormous, hundreds of times the size of the Sun, its atmosphere reaches even farther into space. This extended outer layer is not just an inactive shell of gas. Instead, it is constantly in motion, shaped by powerful convection currents rising from the star's interior. These currents create hotspots on the surface. However, rather than forming a simple expanding cloud, the material released into Betelgeuse's atmosphere appears to be arranged in unexpected layers and clumps, suggesting that complex forces are at work. Infrared and ultraviolet observations of Betelgeuse have revealed temperature variations across its outer layers, with some parts of the atmosphere appearing much hotter than others. This is unusual for a red supergiant, which should have an outer envelope that gradually cools as it extends away from the core. Instead, Betelgeuse's atmosphere is full of irregular heating patterns, with regions that are significantly hotter than expected. One possible explanation is that shockwaves from deep inside the star are traveling outward, compressing and heating certain parts of the atmosphere while leaving others cooler. These shockwaves may be caused by pulsations within the star, as Betelgeuse expands and contracts on a cycle lasting hundreds of days. Each contraction pushes waves of energy outward, stirring up the surrounding gas and causing erratic heating. Betelgeuse has been observed releasing enormous plumes of gas from its atmosphere, some of which extend hundreds of millions of kilometers into space. These outflows are not uniform, but instead occur in specific directions, creating a lopsided and uneven shape around the star. Betelgeuse's stellar wind is unpredictable, sometimes forming dense clouds of gas and dust while leaving other areas relatively clear. The process driving these outflows is still debated, while radiation pressure from the star's intense light may play a role in pushing material away. If Betelgeuse has localized magnetic fields near its surface, they could be funneling gas into specific regions, shaping the star's extended atmosphere in unexpected ways. Observations from telescopes like ALMA or Atacama Large Millimeter Submillimeter Array have detected complex molecules such as carbon monoxide and water vapor, forming within the outer layers of the star. These molecules should not be able to survive in such an energetic environment, yet they are found at great distances from the surface, suggesting that some parts of the atmosphere are much cooler than others. This has led to speculation that the star's atmosphere is not a smooth, gradual gradient from hot to cool, but rather a chaotic mix of different temperature zones. Red supergiants are known to produce large amounts of dust. However, Betelgeuse seems to be forming dust at an unpredictable rate. Some observations suggest that clouds of dust condense rapidly in certain parts of the atmosphere, while other regions remain dust-free. Unlike a steady outflow of dust that might be expected from a star nearing the end of its life, Betelgeuse seems to go through sudden, unpredictable episodes of dust production. Instead of a sharp transition between the star's surface and the surrounding space, the outer layers seem to gradually blend into the interstellar medium. Some measurements suggest that material from Betelgeuse's atmosphere has extended so far that it is mixing with the surrounding gas of the Orion constellation, creating a diffuse and complex structure. This suggests that the process of mass loss in red supergiants is not just a local event around the star, but something that can shape entire regions of space. Recent studies have also suggested that Betelgeuse's outer layers might be rotating differently than expected. While the star as a whole is known to rotate slowly, some evidence hints that certain parts of the atmosphere might be moving at different speeds. This could mean that the outer layers are decoupled from the deeper interior, rotating independently in a process similar to differential rotation seen in the Sun. Traditional models of red supergiants assume that they have relatively smooth, expanding envelopes, but Betelgeuse demonstrates that this may not always be the case. Instead, the outer layers of these massive stars may be far more dynamic, changing shape and structure on short timescales due to pulsations, shock waves, magnetic activity, and mass loss. While its chaotic atmosphere raises many questions, it also offers clues about the processes that occur in the final stages of a star's life. The strange and unpredictable behavior of Betelgeuse may not be an anomaly, but rather a sign that our understanding of red supergiants is still incomplete. Can Betelgeuse become a neutron star instead of a black hole? When Betelgeuse reaches the end of its life, it will explode in a supernova, leaving behind either a neutron star or a black hole. The question is, which one will it become? The fate of a star after its supernova explosion depends on its core mass at the moment of collapse. If Betelgeuse is on the lower end of the mass range for core collapse supernovae, it could become a neutron star. If it is heavier, it might collapse directly into a black hole. But the dividing line between these two outcomes is not always clear, and astronomers are still trying to refine their models to understand what happens in these final moments. Neutron stars are formed when the core of a massive star collapses, but not with enough mass to create a black hole. Instead, the core's protons and electrons are crushed together by gravity, forming neutrons. The result is an object with more mass than the Sun, packed into a sphere only about 20 kilometers wide. The collapse stops because the neutrons provide a force called neutron degeneracy pressure that resists further compression. This is what allows a neutron star to exist rather than collapsing further into a black hole. The key factor in determining whether Betelgeuse will become a neutron star is the mass of its iron core at the time of collapse. As Betelgeuse burns heavier and heavier elements in its final stages, the core builds up iron. Unlike lighter elements, iron does not produce energy when it undergoes fusion. Once the core reaches a critical limit, known as the Chandrasekhar limit, around 1.4 times the mass of the Sun, it can no longer support itself against gravity. If the core is only slightly above this limit, the collapse will be halted by neutron degeneracy pressure, and Betelgeuse will leave behind a neutron star. If the core is significantly more massive, even neutron pressure will not be enough to stop the collapse, and a black hole will form. Right now, the exact mass of Betelgeuse's core is uncertain. Estimates of the star's total mass suggest that it is between 10 and 20 times the mass of the Sun, which places it in the range where both neutron stars and black holes are possible outcomes. Some models suggest that stars in this mass range usually form neutron stars, but others argue that mass loss before the explosion plays a major role. If Betelgeuse has shed enough of its outer layers, the remaining mass at the time of collapse might not be enough to form a black hole. Some red supergiants go through extreme mass loss events shortly before they die, creating vast clouds of gas and dust around them. If Betelgeuse loses enough of its mass this way, it could increase the chances of forming a neutron star instead of a black hole. There is also the possibility of an unusual outcome known as a failed supernova. If Betelgeuse's core is right on the edge of the neutron star, black hole boundary, it might first form a neutron star, but then collapse further into a black hole within seconds or minutes. In this scenario, Betelgeuse's supernova could be much dimmer than expected, as most of the energy would be lost into the newly formed black hole rather than released as light. If Betelgeuse does become a neutron star, it could take on different forms depending on its properties at birth. Some neutron stars become pulsars, spinning rapidly and emitting beams of radiation from their magnetic poles. Others remain quiet, slowly cooling over time without producing much detectable radiation. If Betelgeuse's neutron star were to be a pulsar, it could provide a new target for astronomers studying the remnants of massive stars. Another possibility is that Betelgeuse could become a magnetar, a type of neutron star with an incredibly strong magnetic field. Magnetars are rare, but they are thought to form from neutron stars born with rapid rotation and strong magnetic fields. If Betelgeuse's core has the right conditions, it could leave behind one of these highly energetic objects, which occasionally produce massive bursts of X-rays and gamma rays. The final fate of Betelgeuse also depends on what happens to the material it ejects during the supernova. Some of this material could fall back onto the newly formed neutron star, increasing its mass. If enough material falls back, the neutron star could gain too much mass to remain stable, eventually collapsing into a black hole after all. This process, known as fallback accretion, is another way that borderline mass stars could transition from neutron stars to black holes. Most supernova remnants that have left behind neutron stars are located far away, making them difficult to study in detail. But Betelgeuse is one of the closest massive stars to Earth. If it explodes in the next few thousand years and leaves behind a neutron star, it will be one of the best opportunities we have to study the aftermath of a supernova up close. How close are we to witnessing a nearby supernova? Betelgeuse's inevitable explosion is one of the most anticipated astronomical events of our time, but the exact timing remains a mystery. It could happen tomorrow, or it could take tens of thousands of years. Astronomers are carefully watching for signs that could indicate when the moment is near, using everything from ground-based telescopes to space observatories to keep an eye on its activity. The most promising clues about Betelgeuse's timeline come from its internal processes, which we can only infer from changes in brightness, spectral shifts, and mass loss. One of the key indicators that a supernova is imminent is an increase in neutrino emissions. These nearly massless particles are produced in enormous numbers when a massive star's core collapses. Unlike light, which can be blocked or delayed by the star's outer layers, neutrinos pass straight through, escaping into space before the explosion is visible. If Betelgeuse were to undergo core collapse in the near future, detectors on Earth, such as the Super Kamiokande in Japan and IceCube in Antarctica, would register a sudden spike in neutrino activity. This would be our first warning that the explosion is happening. Another sign astronomers are looking for is a rapid increase in brightness just before the final collapse. As the core becomes unstable, it may send shockwaves outward, briefly causing Betelgeuse to brighten significantly. This could last for days or weeks, giving astronomers a final chance to prepare before the supernova occurs. Space-based telescopes like NASA's James Webb Space Telescope and ESA's Gaia are capable of detecting these changes with high precision, allowing researchers to track the star's final moments in real time. When a red supergiant is close to explosion, its outer layers may become more unstable, leading to shifts in spectral lines. These changes can reveal information about temperature, density, and motion in the star's atmosphere. Observatories like the Very Large Telescope in Chile and the Hubble Space Telescope have been monitoring Betelgeuse's spectrum for years, looking for any unusual shifts that might indicate the star is reaching a critical stage. One of the biggest challenges in predicting Betelgeuse's explosion is our limited knowledge of what happens inside red supergiants in their last moments. While we have observed supernovae in distant galaxies, we have never had the opportunity to study a star this close in such detail before its explosion. Current models suggest that once the core has exhausted its fuel, it will collapse within seconds, but the external layers of the star might take hours or even days to fully react. If Betelgeuse were to explode soon, it would give astronomers an unprecedented look at this process. Catching the supernova as it happens would require constant monitoring. Astronomers already use automated sky surveys like the All-Sky Automated Survey for Supernova and the Zwicky Transient Facility to scan the sky for sudden brightening events. These surveys detect new supernovae in distant galaxies all the time, but having a target as well known as Betelgeuse means they can dedicate more resources to watching it closely. Future projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will provide even more detailed monitoring, scanning the entire sky every few nights to detect any changes. If Betelgeuse does go supernova, the explosion will be one of the brightest celestial events ever seen from Earth. Nighttime observers would see a new star dominating the Orion constellation, and for the first time in human history, people would be able to witness a supernova with the naked eye. The light from the explosion would take about 600 years to reach Earth, meaning the event has already happened. We just haven't seen it yet. Observatories across the world would immediately focus their instruments on it, studying how the explosion evolves over time. Radio telescopes would listen for signals from the expanding shockwave, while X-ray and gamma-ray observatories would detect high-energy radiation from the core collapse. These observations would help astronomers understand how massive stars die and how they enrich the universe with heavy elements. The differences between Betelgeuse and Canis Majoris, two paths to destruction. Betelgeuse and Canis Majoris are two of the most famous red supergiants in the universe. Both are nearing the end of their lifespans, yet their paths to destruction differ in significant ways. Betelgeuse, a relatively young and well-studied supergiant, is known for its unpredictable brightness variations and rapid mass loss. Canis Majoris, on the other hand, is an extreme outlier, a hypergiant whose immense size and violent eruptions make it one of the most unstable stars ever observed. Comparing these two stars provides insight into the different ways massive stars meet their end. While Betelgeuse is already an enormous star, with a radius roughly 1,000 times that of the Sun, Canis Majoris is in another league entirely. At its maximum estimated size, it could stretch anywhere from 1,400 to 2,000 times the Sun's radius, making it one of the largest known stars in terms of sheer volume. If placed in our solar system, Betelgeuse would extend out to the orbit of Jupiter, but Canis Majoris would swallow Saturn and possibly even Uranus. Despite this immense size, both stars have comparable masses, estimated to be between 15 and 25 times the mass of the Sun. The difference lies in their density and structure. Canis Majoris is more extended and diffuse, with a much lower average density than Betelgeuse. Both stars are luminous, but Canis Majoris outshines Betelgeuse by a considerable margin. Betelgeuse has a luminosity around 100,000 times that of the Sun, while Canis Majoris can be up to 300,000 times as bright. This extreme output comes at a cost. Canis Majoris burns through its nuclear fuel at an even faster rate than Betelgeuse, making its lifespan even shorter. While Betelgeuse is expected to have a lifespan of about 10 million years in total, Canis Majoris likely had an even shorter lifetime, possibly under 8 million years. This accelerated burning is typical of the most massive stars, which exhaust their fuel quickly before undergoing a rapid and violent death. Betelgeuse is well known for shedding large amounts of material, most dramatically in the Great Dimming Event of 2019. However, its mass loss rate is moderate compared to the hypergiant, which is losing material at an astonishing rate, possibly up to 100 times faster than Betelgeuse. Its outer layers are constantly being torn away by intense stellar winds, creating an enormous and complex nebula around the star. Observations with the Hubble Space Telescope and other instruments have revealed vast arcs and knots of material surrounding Canis Majoris, indicating that it has undergone multiple large-scale eruptions in its recent history. These ejections suggest that the star is shedding its outer layers in dramatic bursts, possibly as a prelude to its final collapse. Betelgeuse is expected to explode as a Type II supernova when its core collapses under the weight of its own gravity. The explosion will be powerful, but relatively normal compared to other supernova types. VY Canis Majoris, however, might undergo a more complex fate. Because of its extreme instability and high mass loss rate, some astronomers speculate that it could follow an alternative path, such as a failed supernova or even a partial collapse that results in a direct transition into a black hole. If it does explode, the event could be a hypernova, an even more energetic version of a supernova, capable of producing long-duration gamma-ray bursts and extreme amounts of high-energy radiation. Betelgeuse's pulsations cause it to expand and contract, creating cycles of brightening and dimming over months or years. The star has a natural variability that astronomers have been tracking for decades. VY Canis Majoris, in contrast, does not follow the same predictable cycles. Its brightness variations are more chaotic, likely due to the turbulent activity in its outer layers and the continuous ejection of material. These irregular changes make it more difficult to predict when the star might reach its final collapse. Betelgeuse's surroundings are relatively well mapped, showing evidence of past mass loss, but without the extreme complexity seen around VY Canis Majoris. The hypergiant is surrounded by a dense and intricate nebula, filled with clumps of material ejected over thousands of years. This nebula is one of the most detailed examples of a star in its final shedding phase, showing how massive stars lose their outer layers before death. The presence of such an extensive nebula suggests that VY Canis Majoris may already be in the last stages before its explosion, possibly closer to its end than Betelgeuse. Is Betelgeuse a typical red supergiant, or is it an exception? Red supergiants are some of the largest stars by volume, with their outer layers extended into a thin, diffuse atmosphere that can be easily affected by internal and external forces. Most red supergiants share common traits: a reddish hue due to their cooler temperatures, a short lifespan of just a few million years, and a future that almost always ends in a core collapse supernova. Betelgeuse fits most of these criteria. It is in the final stages of its life. Its surface temperature is around 3,500 Kelvin, and it is expected to explode in the near astronomical future. However, when comparing Betelgeuse to other known red supergiants, its deviations from the norm become more apparent. One of the most obvious differences is its extreme brightness variations. While all red supergiants experience some level of variability, Betelgeuse's fluctuations have been particularly dramatic. In the Great Dimming event, Betelgeuse's brightness dropped by nearly 60%. While such events are not unheard of among red supergiants, the scale of Betelgeuse's dimming was unusual, suggesting a level of instability that is not common in stars of its type. Red supergiants are generally expected to spin slowly due to the expansion they undergo when they transition out of their main sequence phase. As a star swells to hundreds of times its original size, conservation of angular momentum dictates that its rotation slows down. However, Betelgeuse is spinning even slower than expected. At its current estimated rotation rate, it takes about 36 years to complete a full rotation, which is much slower than many other red supergiants. While convection-driven surface activity is common in red supergiants, Betelgeuse appears to have unusually large convective cells. Other red supergiants exhibit convection, but the scale and intensity of Betelgeuse's surface activity set it apart. Estimates suggest that it started its life with a mass between 15 and 20 times that of the Sun, which is within the range for red supergiants. However, given its high rate of mass loss, Betelgeuse may have already shed a significant fraction of its original mass. Some researchers have suggested that Betelgeuse might have originally been more massive, possibly closer to 25 solar masses, but has since lost so much material that it now appears less extreme than it once was. If this is the case, its current state might not be representative of most red supergiants, but rather a later stage evolution that only some stars undergo. While red supergiants are not typically thought to have strong magnetic fields, recent studies have suggested that Betelgeuse could possess a localized magnetic field that influences its mass loss and surface activity. Magnetic fields could contribute to the shaping of its circumstellar environment, guiding how material is ejected from the star and how it interacts with surrounding space. If Betelgeuse's magnetic properties are indeed stronger than expected, it could be another factor setting it apart from other red supergiants. Despite these anomalies, Betelgeuse still serves as an important reference point for understanding the evolution of massive stars. Its relative proximity to Earth, only about 640 light-years away, makes it an ideal candidate for detailed observation. Other red supergiants are often too distant to study at the same level of detail. In many ways, Betelgeuse follows the expected trajectory of a dying massive star, but in others, it defies conventional expectations. It might not be a standard example of its class, instead representing a specific type of red supergiant, one that has undergone additional evolutionary processes that have set it apart from the majority of its peers. Supergiant star clusters. Where do the largest stars form? The largest stars in the universe do not form in isolation. They emerge from dense regions of gas and dust where the conditions are just right to give birth to some of the most massive stars ever observed. These environments, known as stellar nurseries, are often found in giant star clusters, collections of stars that form together from the same molecular cloud. Within these clusters, a small fraction of stars grow to extreme sizes, evolving into the luminous supergiants that dominate their surroundings. Massive stars need extreme conditions to form. Unlike smaller stars, which can emerge from relatively modest clouds of gas, supergiants require enormous reservoirs of material. These conditions are found in the largest star-forming regions of galaxies, where turbulence, shock waves, and gravitational interactions compress gas to densities high enough to trigger the birth of the biggest stars. The Orion molecular cloud complex, for example, is one of the most active stellar nurseries in the Milky Way, giving rise to many high-mass stars. Though Betelgeuse is located near this region, it is not currently part of a cluster, suggesting it may have formed in a group of stars that has since dispersed. Star clusters that produce supergiants tend to fall into two main categories. The first type, known as open clusters, consists of loosely bound groups of young stars. These clusters are not particularly dense, and over time their stars drift apart due to gravitational interactions. Many of the massive stars that were once part of open clusters have already wandered away, making it difficult to trace their origins. The second type, globular clusters, are much older and contain tens of thousands or even millions of stars packed tightly together. While globular clusters do not produce new stars today, they were once home to some of the most massive stars in the early universe. Some of the most well-known star clusters that have given rise to supergiants include the Tarantula Nebula's R136 cluster, the Westerlund 1 cluster, and the massive Cygnus OB2 association. These clusters contain stars even larger than Betelgeuse, including luminous blue supergiants, Wolf-Rayet stars, and hypergiants. The environments in these clusters are incredibly energetic, filled with ultraviolet radiation, intense stellar winds, and strong magnetic fields. These factors shape the evolution of massive stars from the moment they are born, influencing how fast they burn through their fuel and how quickly they shed mass. The process of forming a supergiant begins when a dense core of gas within a molecular cloud starts to collapse under its own gravity. As the core contracts, it heats up, eventually reaching the temperatures necessary to ignite nuclear fusion. At this stage, the forming star is surrounded by a thick envelope of gas and dust, which it continues to accumulate. The more material it gathers, the more massive it becomes. However, this process has limits. If a star becomes too massive, the intense radiation it produces pushes against the surrounding gas, preventing further growth. This radiation pressure plays a crucial role in determining the maximum possible mass of a star. As a massive star ages, it expands and cools, eventually evolving into a supergiant. At this stage, it becomes one of the most luminous objects in its cluster, outshining nearly all of its neighbors. However, supergiants do not stay in clusters indefinitely. Over time, gravitational interactions with other stars can cause them to drift away, separating them from their birthplaces. The movement of massive stars away from their original clusters leads them to becoming runaway stars. Some of these stars may have been ejected from their clusters due to gravitational interactions with other stars, while others may have been propelled by the explosion of a nearby supernova. In the Milky Way, some of the most massive young clusters are still actively forming new stars, creating the next generation of supergiants. The Carina Nebula, for example, contains stars that will one day become red supergiants, like Betelgeuse, eventually ending their lives in spectacular explosions. Observing these clusters gives astronomers valuable insights into the early lives of massive stars, helping them understand the conditions that lead to the formation of such objects. Are we underestimating the size of the largest stars? Unlike planets or smaller stars, which have well-defined surfaces, supergiants are vast, diffuse, and often shrouded in thick layers of gas and dust. Their outer edges are not clearly defined, and their atmospheres extend far into space, making it difficult to determine their true size. As a result, astronomers rely on a combination of techniques to estimate their diameters, but recent studies suggest that these measurements might be underestimating just how massive these stars truly are. Traditional methods of measuring stellar size involve studying how a star's light dims when it passes behind another object, or using interferometry, which combines signals from multiple telescopes to create a high-resolution image. These techniques have provided rough estimates for the sizes of stars like Betelgeuse, VY Canis Majoris, and UY Scuti, all of which are considered some of the largest known supergiants. However, these estimates come with significant uncertainties. Supergiants do not have a solid surface. Their outer layers are composed of convective cells that rise and fall like boiling water. These convective cells cause brightness variations that can be mistaken for changes in size. This makes it difficult to determine the actual size of a star, as its atmosphere is in constant motion, expanding and contracting over time. These stars emit vast amounts of radiation, which ionizes the surrounding gas and creates a diffuse halo of material that extends far beyond what is typically considered the star's surface. This makes it difficult to define the boundary between the star and space, as different wavelengths of light reveal different apparent sizes. In visible light, a supergiant might appear smaller than it does in infrared, where its outer layers become more transparent. This discrepancy suggests that many of the size estimates currently accepted might only represent the densest parts of the star, rather than its full extent. This means that any attempt to measure the diameter of these stars involves choosing an arbitrary threshold, often based on where the star's brightness drops below a certain level. However, different studies use different criteria for defining this threshold, leading to inconsistent size estimates. Some methods define the star's radius as the point where optical depth drops to a specific value, while others use the location where the density of material becomes negligible. These variations mean that a red supergiant can appear significantly larger or smaller depending on how its boundary is defined. One way astronomers attempt to refine their measurements is by studying how a star's brightness changes when it is observed from different angles. This technique, known as limb darkening, takes advantage of the fact that light coming from the center of a star appears brighter than light from its edges. By carefully modeling how the brightness changes across a star's disk, astronomers can make more accurate estimates of its true size. However, this method is complicated by the presence of large-scale surface features, such as star spots and convective cells, which can distort the results. Interferometry has provided some of the most detailed measurements of supergiant stars to date, but even this technique has limitations. The process involves combining light from multiple telescopes to create an image with the resolution of a much larger telescope. While this allows astronomers to see finer details than a single telescope could capture, it also means that any gaps in the data must be filled using models. If a star's outer layers are more extended than expected, or if they contain unexpected structures, these models might not fully capture the star's true size. Future telescopes, such as the Extremely Large Telescope and the 30-meter telescope, will offer much higher resolution, allowing astronomers to directly observe the outer layers of supergiants with unprecedented detail. These instruments will be able to detect subtle variations in brightness, temperature, and composition, helping to refine size estimates and uncover previously unknown features. Another promising approach involves using gravitational microlensing, a phenomenon that occurs when a massive object passes in front of a background star, temporarily magnifying its light. This effect can be used to study the structure of a supergiant's outer layers, providing clues about its true size. While microlensing events involving supergiants are rare, they offer a unique opportunity to measure stellar diameters in a way that is not influenced by the limitations of traditional techniques. One of the biggest uncertainties is caused by dust. Many supergiants are surrounded by thick clouds of dust that can obscure their true size, making them appear smaller than they actually are. This is particularly problematic for stars like VY Canis Majoris, which is known for its extreme mass loss and dense circumstellar environment. If current size estimates are indeed too low, it raises important questions about the evolution of supergiant stars. Larger stars would have even more extended atmospheres, making them more prone to losing mass through stellar winds. This could impact their lifespans, altering predictions about when they will explode as supernovae, or whether they collapse directly into black holes or leave behind neutron stars. Some are even exploring the possibility that certain supergiants might extend so far into space that their outer layers become gravitationally unstable, leading to large-scale shedding of material. If this is the case, it could explain some of the mysterious dimming events seen in stars like Betelgeuse. Such events could be more common than currently believed, suggesting that supergiants are constantly reshaping themselves on much shorter timescales than expected. With new telescopes coming online in the next decade, the mystery of supergiant sizes may finally be solved, offering a clearer picture of these colossal stars. Theoretical exotic matter in red supergiants, a hidden physics playground? With crushing densities, mind-bending temperatures, and pressures far beyond anything experienced on Earth, the interiors of red supergiants create the perfect setting for testing the limits of physics. The standard model of stellar evolution describes these interiors as dominated by fusion, with elements like helium, carbon, and oxygen forming in progressive layers as the star ages. But some theories go further, suggesting that the extreme conditions inside red supergiants might allow for the existence of exotic forms of matter. Strange matter is a hypothetical substance containing a type of quark called a strange quark, which is not found in ordinary atomic nuclei. Normally, matter is built from up and down quarks, the two fundamental building blocks of protons and neutrons. But under extreme pressure, some theories suggest that a transformation could occur, where up and down quarks rearrange into strange quarks, creating an entirely new kind of matter. If such a process were possible in red supergiants, their cores might contain an exotic mixture of normal nuclear material and strange matter, fundamentally altering how they evolve and explode. Some models propose that if enough strange matter were present in the core of a red supergiant, it could affect the way the star collapses at the end of its life. Instead of a traditional supernova that leaves behind a neutron star or black hole, a star with strange matter might form an object known as a quark star. These hypothetical stars, if they exist, would be made almost entirely of deconfined quarks rather than traditional neutrons. No confirmed quark stars have been found, but some astronomers suspect that certain unusually dense neutron stars could be candidates. Another possibility is that the deep cores of red supergiants could briefly reach conditions where exotic phases of nuclear matter emerge. At high enough temperatures, atomic nuclei may no longer be distinct, forming what's called a pion condensate, a state in which particles known as pions, usually found fleetingly in particle accelerators, dominate the interactions between nucleons. Such a phase could alter the behavior of the core, affecting how the star transitions from fusion to collapse. If this kind of matter plays a role in supernovae, it could explain some of the variations seen in different explosion types. The presence of axions, another hypothetical form of exotic matter, has also been suggested in high-energy astrophysical environments. Axions are theoretical particles that might solve some outstanding problems in quantum physics, particularly related to the strong nuclear force. If axions exist, they could be produced in the cores of red supergiants and escape into space, carrying energy away from the star. This energy loss mechanism could accelerate the evolution of a star, causing it to reach the end of its life faster than expected. Magnetic monopoles, if they exist, would be single magnetic poles, either north or south, unlike normal magnets, which always have both. Some theories suggest that these monopoles could be created in extreme astrophysical conditions and influence how magnetic fields behave in stars. If supergiants contain even a tiny fraction of magnetic monopoles, their internal magnetic structure could be unlike anything currently modeled, potentially influencing how mass loss occurs, or how the star's core eventually collapses. Dark matter, which makes up most of the universe's mass, does not interact with ordinary matter in the usual way. It does not emit light or interact electromagnetically. However, if certain types of dark matter particles, such as weakly interacting massive particles, or WIMPs, can interact with normal matter even slightly, they might accumulate in the cores of stars over time. Some theories suggest that if enough dark matter builds up inside a massive star, it could affect the way the star generates energy, altering its expected lifetime, and possibly even changing how it ends its life. Some theories propose that instead of a symmetrical explosion, a star containing exotic matter could collapse unevenly, ejecting material in an unusual pattern or producing a highly directional burst of energy. This could explain some of the rare supernovae that don't fit standard predictions, such as supernovae that produce extremely bright or extremely faint remnants, or those that seem to occur in multiple stages rather than a single explosion. One of the biggest challenges in exploring these possibilities is that exotic matter, by definition, isn't something we can easily detect in normal conditions. Most of these ideas rely on indirect evidence, looking for unusual behavior in stars or unexplained deviations from expected models. However, new observational techniques, including more detailed neutrino detection and gravitational wave studies, could provide clues. If a nearby supergiant like Betelgeuse were to explode, the data collected from such an event could test whether exotic matter played any role in its collapse. What if Betelgeuse had a Dyson sphere built around it? If an advanced civilization were capable of constructing a Dyson sphere around Betelgeuse, it would be one of the most ambitious engineering projects imaginable. A Dyson sphere, first proposed by physicist Freeman Dyson in 1960, is a hypothetical megastructure designed to capture a star's energy output, potentially providing nearly limitless power. The idea is often used in science fiction, but in principle, a sufficiently advanced species with the capability to manipulate stellar-scale structures might attempt such a feat. If Betelgeuse were surrounded by such a structure, it would radically change the way humans perceive the star. First, there would be a dramatic drop in visible light output. A fully enclosed Dyson sphere would completely block the star's radiation from reaching us, making Betelgeuse disappear from the sky. However, if the structure were a more fragmented or incomplete version, such as a Dyson swarm, which consists of thousands or millions of orbiting solar collectors, it might dim the star intermittently. This could mimic some of the irregular dimming events observed in Betelgeuse. While dust clouds and convective activity ultimately provided a more conventional explanation, a partial Dyson swarm could, in theory, create similar observational effects. The star emits vast amounts of energy, mostly in infrared wavelengths due to its relatively cool surface temperature. A Dyson sphere would not eliminate this energy, but would instead absorb it and re-radiate it at even lower temperatures, likely in the far infrared spectrum. This means that while the star's visible light might be obscured, astronomers using infrared telescopes could detect a strange excess of infrared radiation from its location, an effect that has been proposed as a way to search for advanced extraterrestrial civilizations. If an intelligent species had the ability to construct such a megastructure, they would need materials on an unimaginable scale. A Dyson sphere would require an immense quantity of raw material, likely harvested from moons, asteroids, or even entire planets. Given Betelgeuse's position in the Orion constellation, surrounded by interstellar gas and potential stellar nurseries, a civilization might have access to resources that could be repurposed for megastructural construction. However, they would also face extreme challenges due to Betelgeuse's instability. The star is constantly shedding mass and undergoing massive convective shifts. Building a Dyson sphere around such a dynamic and unpredictable star would be significantly harder than surrounding a stable, main-sequence star like the Sun. A fully enclosed Dyson sphere might be completely destroyed when Betelgeuse collapses, releasing an enormous burst of energy capable of ripping apart even the strongest materials. If an advanced species had built such a structure, they would likely have planned for this event, either by evacuating the sphere, dismantling parts of it, or using technology far beyond human understanding to stabilize the star in some way. Some even suggest that a sufficiently advanced civilization could manipulate stellar evolution, preventing a supernova or even harnessing its energy for other purposes. Beyond energy collection, a Dyson sphere around Betelgeuse could serve other purposes. It might act as a gigantic stellar observatory for a civilization studying extreme astrophysical conditions. Red supergiants like Betelgeuse experience chaotic internal processes, and an advanced society might have developed ways to control or modify these processes for scientific research. They might even be attempting to alter the timeline of Betelgeuse's supernova, delaying or accelerating its collapse for reasons we can only speculate about. Another possibility is that a Dyson sphere around Betelgeuse could function as a massive habitat, providing living space for a civilization that prefers, or is adapted to, living in artificial structures rather than planets. If constructed with enough efficiency, the inner surface of such a sphere could house trillions of individuals, using the star's energy to sustain an artificial ecosystem. This kind of structure would turn Betelgeuse into the center of an entire artificial world, potentially home to a vast and advanced society. Astronomers looking for signs of extraterrestrial intelligence often focus on stars with unexplained infrared excesses, which could indicate artificial heat re-radiation from megastructures. If a future survey found that Betelgeuse's infrared emission was unusually high, or displayed patterns inconsistent with natural stellar processes, it could be a sign of something artificial. Additionally, if Betelgeuse's light variations became even more irregular in ways that dust and natural stellar activity couldn't fully explain, it might prompt further investigation into non-natural causes. There are also more speculative ideas about how a Dyson sphere could be used as a signaling device. If an advanced civilization wanted to communicate with others across the galaxy, they might modulate the amount of light escaping from the structure, effectively turning the star into a giant cosmic beacon. By controlling the pattern of visible and infrared emissions, they could send intentional signals across interstellar distances, potentially detectable by future human technology. Could a supernova like Betelgeuse's ignite life on a nearby planet? When Betelgeuse eventually reaches the end of its life and explodes, it will send shockwaves rippling through space, unleashing intense radiation and heavy elements into its surroundings. At first glance, it might seem like a supernova could only bring destruction to any nearby planets. The sheer force of the explosion would strip atmospheres, bombard surfaces with lethal radiation, and destabilize planetary environments. However, some scientists have speculated that such an event could also have the opposite effect, it could potentially ignite the conditions needed for life to emerge or evolve in unexpected ways. One of the most important ingredients for life as we know it is complex chemistry, and supernovae are some of the greatest chemical factories in the universe. Elements like carbon, oxygen, nitrogen, phosphorus, and sulfur, key building blocks of biological molecules, are forged in these stellar deaths. Even more significantly, supernovae produce and distribute iron, cobalt, and other heavy elements, scattering them into interstellar space, where they can eventually become part of planets, moons, or even life itself. The creation of these elements alone, however, is not enough. For life to emerge, these raw materials need to be assembled into complex molecules, and that is where the energy released by a supernova could play a crucial role. The powerful shockwaves from the explosion would travel outward at incredible speeds, compressing gas and dust clouds in their path. This compression can trigger star formation, leading to new planetary systems where the elements from the exploded star become part of new worlds. If these planets form within the habitable zones of their stars, they might have the right conditions for liquid water, which is essential for life as we understand it. But what about planets that already exist when a nearby supernova occurs? If a world is within a few dozen light-years of the explosion, the radiation from the blast could be devastating. High-energy gamma rays and X-rays would rip through atmospheres, breaking apart molecules and stripping away protective ozone layers. If the planet had life on its surface, it might experience mass extinctions as ultraviolet radiation from its own star suddenly becomes deadly without an ozone shield. However, if life were present underground or beneath an ocean, it might be shielded from the worst effects, potentially surviving through the supernova's aftermath. There is also the possibility that the intense radiation and energy from a supernova could create the right conditions for new biochemical processes to begin. On Earth, ultraviolet light and high-energy particles have been proposed as triggers for prebiotic chemistry, the processes that led to the first self-replicating molecules. If a planet were at just the right distance, the radiation from Betelgeuse's explosion might provide a similar spark, breaking apart simple molecules and allowing them to reform into more complex organic structures. This could serve as a catalyst for life, setting off chemical reactions that might not have otherwise occurred in a more stable environment. Another way a supernova could influence life is through cosmic rays, high-energy particles accelerated to nearly the speed of light. When these particles strike an atmosphere or surface, they can cause mutations in DNA or other genetic material. While too much radiation would be lethal, a controlled amount of mutations could drive evolution forward, introducing changes that might help life adapt to new conditions. On Earth, some researchers have suggested that past supernovae may have played a role in shaping evolution by periodically increasing mutation rates. If Betelgeuse were close enough when it explodes, but not close enough to completely sterilize a planet, it could create such an environment. A supernova also releases massive amounts of dust and gas, which can drift through space for millions of years. If some of this material were to land on a planet, it could enrich the environment with elements that were previously rare. For example, phosphorus is an essential element for life on Earth, playing a key role in DNA, cell membranes, and energy transfer. An explosion that scattered phosphorus, iron, and other biologically useful elements onto a nearby world could make that planet more chemically rich and potentially more suitable for life in the long term. There is another intriguing possibility. What if life already existed near Betelgeuse, but in a dormant state? Some microbial life forms on Earth are known to survive in extreme conditions, remaining dormant for thousands or even millions of years until conditions improve. If an alien world near Betelgeuse had microbial life buried beneath the surface or trapped in ice, the energy from a supernova could melt ice, release trapped gases, or heat subsurface environments enough to wake up dormant organisms. In this way, rather than creating life from scratch, a supernova could serve as the trigger that brings an existing but inactive biosphere back to life. If a planet were on the outer edge of Betelgeuse's supernova blast zone, it might experience dramatic climate changes due to the sudden influx of heat and radiation. This could lead to new environmental pressures. The early Earth went through extreme environmental changes, from ice ages to volcanic activity, which may have helped drive evolution forward by forcing life to adapt to shifting conditions. A supernova could create a similar effect on an alien world, acting as a cosmic reset button that reshapes the evolutionary landscape. While the full impact of such events is still uncertain, they are a reminder that life and destruction are often closely linked in the cosmos. A supernova is an ending, but also a beginning, scattering the ingredients for future stars, planets, and possibly even new forms of life across the galaxy. Are red supergiants more chaotic than we thought? Fractals in star structures. Unlike the Sun, which has a relatively well-defined surface with structured convection cells, red supergiants display vast, unpredictable patterns of activity. The star's outer layers boil and churn in ways that seem almost chaotic, with massive convective currents that rise and fall over time, shifting the star's shape and brightness in irregular ways. Observations suggest that these patterns may not be entirely random, but instead follow principles found in fractal geometry and chaos theory, branches of mathematics that describe complex self-similar patterns found in nature. Chaos in stellar structures begins deep within the star. A red supergiant is no longer in the stable phase of its life, where hydrogen fuses into helium in a controlled, steady manner. Instead, nuclear reactions take place in different layers, with fusion shifting between helium, carbon, oxygen, and eventually heavier elements. This layered burning process is not smooth. It creates instability, with energy being produced in uneven bursts rather than a continuous flow. Unlike the well-organized energy transport inside a main sequence star like the Sun, energy in a red supergiant moves outward in enormous turbulent convective currents. These currents are so vast that a single convective cell can be millions of kilometers across, larger than the orbits of some planets in our solar system. This turbulence does not follow simple, predictable patterns. Instead, it exhibits characteristics of fractals, structures that look similar at different scales. Fractals are found throughout nature, from the branching patterns of trees to the structure of clouds, and even the distribution of galaxies. In a red supergiant, the chaotic convective flows appear to break apart into smaller eddies and currents, each resembling the larger patterns. The reason for this lies in the way energy moves through the star's plasma. The outer layers of Betelgeuse, for example, do not behave like a solid object, but more like a fluid, subject to complex instabilities that form smaller structures within larger ones. This gives rise to surface features that appear random, but may actually follow deeper mathematical rules. One consequence of this chaotic structure is that the surface of a red supergiant is always changing. Bright spots and dark patches appear and disappear unpredictably. This explains why Betelgeuse's brightness can vary in ways that are difficult to predict. Unlike a Cepheid variable star, which pulses in a regular cycle due to a clear physical mechanism, Betelgeuse's dimming and brightening seem almost erratic. Fractal-like behavior in stars is not limited to their surfaces. It extends to the way matter is expelled into space. Instead of a uniform outflow, the ejected stellar wind appears to form intricate swirling patterns, resembling the complex structures seen in smoke or fluid turbulence. Infrared observations of Betelgeuse's surrounding material reveal an uneven, clumpy distribution of gas and dust, rather than the smooth shell that older models predicted. This suggests that the same chaotic processes affecting the star's surface are also shaping its stellar winds, creating outflows that are highly structured and asymmetric. Chaos theory, which was originally developed to describe unpredictable systems like weather patterns, may help explain why red supergiants behave this way. In chaotic systems, small changes in initial conditions can lead to vastly different outcomes, a concept often called the butterfly effect. In a red supergiant, even a slight variation in the way energy moves through its convective layers could result in dramatically different surface features. This could explain why some red supergiants exhibit extreme mass loss, while others remain relatively stable. A direct consequence of this chaotic behavior is that predicting when a star like Betelgeuse will explode is extremely difficult. Because of the complex interactions within its interior, small fluctuations in fusion rates or convective currents could either speed up or delay its final collapse. This makes it challenging to determine whether an observed change in brightness is an early warning of a supernova or just another temporary fluctuation caused by surface turbulence. The study of fractal structures in red supergiants is still in its early stages. Simulations of stellar interiors are becoming more sophisticated, incorporating chaotic dynamics to better predict how these stars evolve. If the fractal nature of red supergiants is confirmed, it could change the way we understand the late stages of massive star evolution, showing that these stars are dynamic, ever-changing systems governed by deep mathematical principles. Could quantum effects play a role in the strange behavior of supergiants? On the surface, these massive stars seem to follow the expected rules of classical physics, with their size, mass loss, and fusion cycles behaving according to well-understood principles. However, as astronomers study these enormous stars in greater detail, certain unpredictable behaviors suggest that something more complex is at play. Some speculate that, even on these vast cosmic scales, quantum effects may influence the behavior of supergiants in ways that have yet to be fully explored. At first glance, quantum mechanics and supergiant stars seem like entirely separate domains. Quantum mechanics governs the world of the very small, atoms, subatomic particles, and fundamental forces that work on tiny scales. In contrast, supergiants are among the largest structures in the universe, spanning hundreds of millions of kilometers. However, the extreme conditions inside these stars, such as the densities found in their cores, the exotic behavior of electrons under immense pressure, and the delicate balance between radiation and gravity, might allow quantum effects to emerge in unexpected ways. Supergiants rely on a complex process to transport energy from their hot cores to their extended outer layers. In smaller stars like the Sun, this is a well-defined process. Energy moves outward through radiation, where photons gradually work their way from the core to the surface, or through convection, where hot plasma rises and cooler plasma sinks. In supergiants, however, the enormous size of the outer layers leads to unpredictable turbulent energy transport. Some researchers suggest that quantum tunneling, an effect where particles can pass through barriers they normally wouldn't be able to, could help explain how energy moves through dense stellar interiors in ways classical physics struggles to model. Another possible quantum influence involves the behavior of electrons under the extreme pressures found in a supergiant's core. Normally, electrons are bound to atoms, but under high temperatures and densities, they form a free-floating sea of charged particles. This leads to a phenomenon known as electron degeneracy, where quantum mechanical rules prevent electrons from being squeezed into the same state. This degeneracy pressure plays a crucial role in the fate of stars, especially in white dwarfs and neutron stars, where it can temporarily hold back gravitational collapse. In a supergiant like Betelgeuse, similar quantum effects could subtly influence how pressure is distributed within the star, affecting its overall stability and the way it loses mass over time. Some scientists also speculate that quantum entanglement, the strange phenomenon where two particles remain connected across vast distances, could have subtle effects in the nuclear fusion process at a star's core. Normally, for fusion to occur, atomic nuclei need to get close enough for the strong nuclear force to overcome their natural repulsion. This requires immense temperatures and pressure. However, some studies suggest that quantum tunneling allows nuclei to fuse at lower energies than classical physics predicts. If entanglement plays a role in this process, it could introduce variations in how energy is produced, leading to unexpected fluctuations in the star's brightness or temperature. Supergiant cells create large hotspots on the star's surface. Observations of Betelgeuse show that these hotspots shift and change in ways that don't entirely match classical predictions. Some researchers have suggested that quantum effects in plasma dynamics, such as wave-particle interactions that influence how charged particles move, could be responsible for some of these unpredictable surface changes. In smaller stars, quantum effects play a role in the way charged particles generate and sustain magnetic fields. If similar processes occur in Betelgeuse, they could affect its stellar winds, its mass loss, and even how material is distributed in its outer layers. The study of quantum effects in astrophysical objects is still in its early stages, but experiments on Earth are beginning to reveal how quantum mechanics might operate under extreme conditions. High-energy particle accelerators can recreate some of the pressures and temperatures found inside stars, offering insights into how nuclear reactions might behave differently when quantum effects are taken into account. Similarly, laboratory studies of plasma physics, where charged particles move in chaotic magnetic environments, could help explain some of the strange behavior seen in supergiant surfaces. Betelgeuse's core. Could there be an exotic fusion process at work? Ordinarily, a star like Betelgeuse follows a well-known sequence of fusion stages. In its earlier life, it primarily fused hydrogen into helium, just like the Sun does today. But as the star aged and hydrogen ran low in the core, the intense gravitational pressure caused the core to contract and heat up, allowing helium to fuse into heavier elements. As Betelgeuse nears the end of its life, it cycles through increasingly advanced fusion processes, fusing heavier and heavier elements until it reaches iron. When that moment arrives, the star will collapse and explode as a supernova. However, there are signs that Betelgeuse may not be following this path exactly as expected. There are hints that something different is occurring in its core, something that isn't entirely explained by standard fusion models. Perhaps Betelgeuse is undergoing an exotic fusion process, one that might not normally occur under standard stellar conditions. Normally, stars only fuse carbon and oxygen after they have fully exhausted their helium supply. But if Betelgeuse has an unusually high concentration of certain isotopes, versions of elements with extra or fewer neutrons, it might be able to sustain different fusion reactions at lower temperatures than normal. This could mean that Betelgeuse's core is producing energy in ways that aren't typically seen in other red supergiants. In extreme environments, free neutrons, uncharged subatomic particles, can sometimes help drive nuclear reactions by allowing atomic nuclei to combine more easily than they would otherwise. Some models suggest that stars with particularly turbulent cores, like Betelgeuse, might be able to generate pockets where neutron-catalyzed reactions briefly take place. If this were happening, it could lead to unpredictable bursts of energy production, possibly explaining some of Betelgeuse's erratic behavior. Betelgeuse's unusually fast helium-burning phase has also puzzled astronomers. Based on current models, it appears that Betelgeuse is burning through its helium supply faster than expected for a star of its mass and size. This suggests that either the star is more evolved than previously thought, or that some additional process is accelerating its core reactions. Some have proposed that magnetic fields deep within Betelgeuse's core could be influencing the fusion process by changing how heat and pressure are distributed, effectively making fusion more efficient than normal models predict. Observing the interior of a star like Betelgeuse is extremely difficult, but scientists are using new tools to probe its hidden depths. One of these is a technique known as asteroseismology, which studies the way sound waves travel through a star's interior. By analyzing the star's subtle pulsations, researchers can infer details about its internal structure and composition. If Betelgeuse is experiencing unusual fusion processes, these methods might reveal unexpected patterns in how its interior behaves over time. If Betelgeuse is experiencing an exotic fusion process, its neutrino output might also differ from what astronomers expect, based on standard models. If researchers can confirm that an exotic fusion process is at work, it could force a revision of our understanding of how massive stars evolve and die. Studying Betelgeuse's core might open new windows into the fundamental processes that govern the life cycles of the most massive stars in the universe. Could neutrino observations reveal when Betelgeuse will explode? Long before Betelgeuse erupts in a supernova, it may start sending out subtle but detectable warnings. These warnings wouldn't come in the form of a sudden brightening or a visible change in its shape. Instead, they would arrive as a quiet flood of neutrinos. Neutrinos slip through almost everything in their path, escaping from deep within the star's core long before its surface shows any sign of impending collapse. If astronomers can decode the patterns of neutrino emissions coming from Betelgeuse, they may be able to predict exactly when the star will explode. Neutrinos are produced in massive numbers inside stars as a natural part of the nuclear fusion process. As long as Betelgeuse is still burning lighter elements like helium, carbon, and oxygen in its core, it will continue emitting a steady but relatively low flux of neutrinos. But as it nears the final stages of its life, the fusion reactions in its core will accelerate and shift to heavier elements like silicon and iron. This phase, which could last anywhere from months to just days before collapse, will dramatically increase neutrino production. Unlike the eventual burst of neutrinos that would accompany a supernova itself, this gradual increase could serve as a long-term warning signal that the star is nearing its end. Some of the world's most advanced neutrino detectors, such as Super Kamiokande and IceCube, are constantly scanning for neutrinos from space. If Betelgeuse were to enter its final stages, these observatories might start detecting a steady increase in neutrinos long before the star visibly changes. Because neutrinos are nearly impossible to stop, they would reach Earth instantaneously, providing real-time updates on what's happening inside Betelgeuse's core. This could give astronomers a chance to monitor the star in unprecedented detail during its final days, preparing for the moment when the light of the explosion finally breaks free. The transition to ion fusion is a particularly crucial moment. Unlike earlier fusion reactions, which release energy and keep the star's core from collapsing, ion fusion actually consumes energy. Once Betelgeuse starts producing iron at a significant rate, the end is near. At this stage, the core will continue to shrink under its own gravity, reaching densities so extreme that even the repulsion between atomic nuclei is no longer enough to resist collapse. When this happens, neutrino production will spike to unimaginable levels, signaling that the star has only seconds left before it implodes. This moment is key because the final burst of neutrinos will precede the visible explosion by several hours. During those last moments, neutrinos will escape the collapsing core instantly, while photons will remain trapped inside for a brief but crucial period. The collapsing layers of the star will generate shock waves that take time to work their way outward before breaking through the outer shell in a dramatic flash of light. By detecting the final burst of neutrinos in advance, scientists could issue an immediate alert that Betelgeuse is now in the process of exploding. In 1987, when a supernova exploded in the Large Magellanic Cloud, neutrino detectors on Earth picked up a sudden burst of neutrinos hours before the visible explosion reached us. That event, known as SN 1987A, confirmed that neutrinos escape a collapsing star before any other detectable signal. However, because that supernova occurred 168,000 light-years away, only about 24 neutrinos were detected. If Betelgeuse were to undergo a similar collapse, it would be much closer, just 642 light-years away, meaning neutrino observatories could detect tens of thousands of neutrinos, providing an even clearer signal. Some models suggest that as the core contracts, its rotation speed could increase dramatically, affecting the way neutrinos are emitted. If a star's core were spinning rapidly just before collapse, the neutrinos escaping from it might show a directional preference, creating a detectable pattern. If astronomers could measure this effect, they might be able to determine not only that a collapse is imminent, but also how it might unfold, whether the explosion would be symmetric or if it could be skewed by the star's rotation. A challenge in using neutrinos to predict Betelgeuse's fate is distinguishing its signals from the background noise of neutrinos constantly streaming through Earth. The Sun itself produces vast numbers of neutrinos as a byproduct of nuclear fusion, and distant supernovae add a steady trickle of neutrinos from across the universe. However, because Betelgeuse is so close, its neutrinos would appear with much higher intensity than anything else in the sky, making them stand out in existing detectors. Future advancements in neutrino astronomy could make this kind of prediction even more precise. Next-generation detectors, such as the Hyper-Kamiokande project in Japan and proposed upgrades to IceCube, will be able to detect lower-energy neutrinos with greater accuracy. This could allow scientists to track subtle shifts in neutrino production inside Betelgeuse years before its final explosion, giving an unprecedented look at the late-stage life cycle of a massive star. Other massive stars throughout the galaxy are reaching the ends of their lives, and the ability to track their final stages through neutrino emissions could lead to incredible breakthroughs in astronomy. If Betelgeuse does give us this rare opportunity, the information gained from its neutrinos would offer insight not just into its own fate, but into the broader life cycle of the universe's most massive stars. Would Betelgeuse's supernova trigger a chain reaction in the Orion arm? When Betelgeuse finally reaches the end of its life and erupts in a supernova, the explosion will be one of the most powerful events in the Orion arm of the Milky Way. The sheer energy released in those final moments will be staggering, sending out shockwaves traveling at thousands of kilometers per second, pushing against the interstellar medium like ripples from a stone dropped into a still pond. But could this explosion be more than a singular event? Could the blast from Betelgeuse set off a chain reaction, influencing other stars and triggering a sequence of events that changes this entire region of space? Supernovae are not isolated occurrences. They often happen in clusters, particularly in regions rich in massive stars like Orion. These stars form together in giant molecular clouds, and as they live and die, they affect one another in ways that shape the future of their stellar neighborhood. The death of Betelgeuse will send shockwaves outward, compressing gas and dust as it moves through space. In the vast Orion molecular cloud complex, an enormous region of star-forming material stretching hundreds of light-years, the presence of supernovae has played a crucial role in shaping its structure. The famous Orion Nebula, visible even to the naked eye on a clear night, is an active stellar nursery where new stars are being born. The entire region is filled with cold gas that, given the right push, could form even more stars. The shockwave from Betelgeuse's explosion might be just the push it needs. If the wavefront of high-energy particles and radiation reaches one of these cold clouds, it could send it over the edge, accelerating the birth of new suns. Astronomers have seen evidence of this kind of chain reaction before. In regions like the Carina Nebula, massive stars have exploded and left behind intricate bubble-like structures in the surrounding gas. Some of these bubbles have bright rims where shockwaves have collided with denser regions, sparking the formation of new stars. If something similar happens after Betelgeuse's explosion, the Orion arm could see a spike in stellar birth rates over the next few million years. Instead of igniting new stars, Betelgeuse's explosion could also disrupt existing systems. Planets orbiting nearby stars might be affected by the blast of radiation and particles, particularly if they lack strong magnetic fields or thick atmospheres to shield them. In extreme cases, the intense wave of high-energy particles could strip away atmospheres or even disrupt the gravitational balance of loosely held planets. There is also the question of whether Betelgeuse's collapse could generate a gamma-ray burst. These bursts typically occur when a massive star collapses in just the right way. If it spins fast enough and channels its energy into twin beams of high-intensity radiation. While Betelgeuse is not expected to produce a long-duration gamma-ray burst due to its rotation rate, even a weaker jet of high-energy radiation could have an impact on any nearby systems directly in its path. The Orion arm, while vast, is not empty. Other stars, some forming, some nearing the end of their lives, dot the landscape of interstellar space. If Betelgeuse's explosion shakes up its local environment, it might contribute to a longer chain of events that reshapes this region. There is even a small chance that nearby supergiants, already unstable in their late stages, could be influenced by the shockwave. A star on the verge of collapse might be nudged over the edge by the energy passing through space, accelerating its own timeline towards supernova. Some of the most dramatic examples of chain reaction star formation have been seen in massive stellar clusters, where multiple supernovae have carved out enormous cavities in space. The famous Tarantula Nebula in the Large Magellanic Cloud is one such region, where the deaths of massive stars have fueled waves of new star formation. While Betelgeuse is more isolated than the stars in these tightly packed regions, its explosion will still contribute to the ever-changing landscape of the Orion Arm. The energy it releases will ripple outward, influencing its neighbors in ways that might not fully manifest for thousands or even millions of years. The Orion Arm itself has been shaped by countless stars before Betelgeuse, and it will continue to evolve long after it is gone. But for a brief moment, when it finally erupts, Betelgeuse will take center stage in this ongoing cosmic drama, sending out a shockwave that could alter the future of this entire region. And on that note, this voyage comes to a close. What would you like for us to cover next? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.